Okay, so we're back with question 8, right? So this is from section B. So actually, you can possibly, you need to answer 2 questions, but we'll just be going through all 3. Okay, so you're given this circuit, right? Charging up the capacitor, and initially the capacitor is uncharged, and after that, after that, the switch is closed at time t equals to 0. So first question, what is the maximum charge that the capacitor can hold in terms of these terms above? So let's think of what it means for a maximum charge, right? That means no additional charge is flowing into the capacitor. And when does that happen? Right? The capacitor stops charging when your current I equals to 0, right? So initially there's some current, and as long as there's current flowing through the circuit, right, the capacitor is constantly charging, right? But the moment when I reaches 0, right, that is when your capacitor is no longer increasing in charge. The charge is no longer flowing into the 2 plates of the capacitor, right, and it holds its maximum charge. So when is your I equal to 0, right? So you have a potential difference across the battery here. It's always going to want to have supply that kind of PD, right? So that we know that the EMF is E, right? And there's also going to be a potential difference across the capacitor when it is charged. So when it is charged, the charge across it is going to increase, and as you squeeze more and more charges, it's going to want to push back. It's going to want to push it's going to develop a PD across its 2 plates as well. And so this PD, right, yeah, it's going to develop ED. So when would the current I equals to 0 is precisely when the capacitor develops the PD, which is equals to E. And the reason is because then in the circuit, right, the resistor will see 0 PD across it, right, because you have your E here, and then you have your E here connected in the opposite direction, right, caused by the charged capacitor, and as a result, they cancel out. So going in one round, right, you don't have any PD across any components, and as a result, your current is 0. So that happens when your PD across the capacitor reaches E, that is when your capacitor stops charging, because there'll be no current flowing through the circuit anymore, since the E here cancels with the E here, right? So yeah, so when your capacitor has the E, how much charge is across it, so we can use, so now we know that the formula is Q equals to CV, where V is the potential difference across the capacitor. So the answer over here is just going to be, Q max equals to the maximum charge you can possibly have is the capacitance C times the PD when it's maximally charged, which is E. So that is your answer for part AI. Okay, so yeah. Okay, so let's move on to the next part. Okay, so on the set of axes, right, we need to sketch 2 graphs. On the first graph, we need to state how the capacitor would change, how the charge across the capacitor would vary with period of time, and mark the value when it's at maximum charge. And the second one, we want to understand the current. Okay, so as the capacitor is charging, it will follow a differential equation, right? So yeah, to formulate it, you look at the differential equation, and then you get an exponentially decaying current. So I'll go through that in another detail. I'll go through that in detail in another video. Or should I do it here? Okay, I'll leave it for another time. But just know that in the end, right, your charge Q as a function of time is going to be equals to the maximum charge at the end, right, times 1 minus e to the power of minus t over RC. Okay, so if you plot this out, right, then you see that Q as a function of time looks something like that, right? And it's asymptotes, right? It asymptotes towards as t approaches infinity, right? Then this term approaches 1, no, it approaches 0, right? It approaches 0, and your Q approaches Q max as t approaches infinity. So it's always asymptoting to us, but because this is never exactly 0, strictly speaking, right, you never actually reach the maximum charge, but it just asymptotes towards it until it's super close, right? And yeah, so when they tell us to mark the value for maximum charge, right? So CE, that's that over there, and yeah, so it asymptotes towards it. It just need to show that it draws closer and closer. Okay, so now the second graph, right, calculate how the current varies with respect to time. Now we know that the current is the change of is the flow of charge. So imagine if you're in your capacitor over here, right? How much charge is across it, right? The charge increases with your current. So your I is actually dq dt. And do note the sign convention over here. Over here is because we have defined I to be equals to I flowing in this direction, which is charging the capacitor. If you had I flowing the opposite direction, then you need to have a minus sign over here. Yeah, but so you can imagine that if your I is positive, right, then the charge across it is increasing. Q is increasing with respect to time, which makes sense, right? But if your I is negative, right, then that means current is flowing the opposite direction. That means your capacitor is losing charge, right? Is um is is dunking the charge back into the circuit. So I is actually just dq dt, which if you differentiate this graph, right, you realize that at very far time, right, is approximately 0. So at very far time is approximately 0, but at the initial time is when your current is the maximum. So if you go ahead and plot it, right, it's going to look something like that. At the asymptote to 0, so actually if you solve it mathematically, then I of t is actually equals to your initial current I naught, right, which is also your maximum current, right, at time t equals to 0, and then e to the power minus t over RC. Yeah, so that's that. Okay, so that's the graphs, right? I'll go into the derivation for this another day. Yeah. Okay, so the next part, right, state an expression for how much energy is stored in the capacitor when the capacitor is fully charged in terms of the terms specified in. So the energy stored in the capacitor is just half CV squared. So when it's fully charged, right, then V is equals to E, so that it's just half CE squared. So I'll go into the derivation for this another time, but it's essentially similar to the inductor video I did previously. I think that was question 4. No, I think that was question 5. Yeah, similar to the derivation. Okay, but how much? Yeah, so that's the answer. So expression for how much work done by the battery in fully charging the capacitor. Okay, so okay, so the work done by the battery, right? There's 2 areas for dissipation, right? One is in the resistor. So when your work done is when your work done by the battery, right? It goes, the work done has to go somewhere, right? And it goes into 1, right? It's dissipated in the resistor as heat, right? And 2 is charged in the capacitor. So yeah, so okay, so in order to find the total work done, we need to do an integral. So the total work done by the battery, right, is going to always instantaneously is going to be equal to I as a function of time and E also as a function of time, but E is just constant, right? And we integrate with respect to dt. So the work done by the battery equals to this thing from time t equals to 0 to the time when it's fully charged, which is actually yeah, I'll just say fully charged, right, at time t equals to infinity. Okay, and you realize that we can do a convenient change of variables, right, using this expression, right? We can do dq over dt e dt, right, from 0 to infinity, time t equals to 0 to infinity. And from here, we're currently working in terms of variables of time, right? But we can change variables to charge by doing by noticing that dt appears in both the numerator and the denominator, so they kind of cancel off. But strictly speaking, mathematically, we're doing a change in variables. So this is going to become e dq. And when we do a change in variables, we need to change the limits of integration as well. So with at time t equals to 0, there's a 0 charge on the capacitor, right? And at time t equals to infinity, it's fully charged. So there's CE charge on the capacitor. Okay. And with that, what's integral of dq, right? E is just a constant, so it's just q, so just eq, right? Evaluated between CE and 0. And you can see that that is naturally CE squared. So yeah, so the answer for this, right, how much work done is by the battery is actually CE squared. So yeah, so this would imply that the power dissipated by the resistor is equals to this quantity minus this quantity is also half CE squared. All right. Okay. So yeah, so okay, next question, right? We have Kershaw's law. You have, so let's just redraw the circuit over here because I don't want to scroll all the way up. So this is your battery, then this is your capacitor, right? And so let's charge Q on the capacitor. So this is actually a derivation for this graph over here, right? Which I didn't go through just now, but we'll go through now. So yeah, so how do we go about doing it? Kershaw's law, let's go in an anti-clockwise fashion. So when you go from minus to a plus, right, you first pick up a plus E, right? You're going from low potential to a high potential, you add E, right? Then now the current is, let's define the current as flowing in an anti-clockwise direction. So current flows I like that, right? So when current flows like this, right, then your resistor is going to have a positive on the upper end and a negative on the lower end because current is flowing downwards. So when you go anti-clockwise, right, jumping from the high potential to the low potential, it's gonna, keeping track of the potential changes, right, it's going to be minus IR. So that's just Ohm's law, right? Then we go from this side, we go from because our the capacitor has a voltage across it that's equals to, right? So we know that Q equals to CV, right? Where V is the potential across it, so that gives us V equals to Q over C. So so this is the potential across the capacitor at any particular charge, right? Q, which is a function of time. So Q is a function of time. So V is also a function of time. C is a constant. So this just gives you. So when you're going, because we define Q such that the left side is positive Q, right? And the right side is minus Q, right? Which we'll see later ties in nicely with our definition of current. So this going from the positive charges to the negative charges, you go from a higher potential to a low potential, gives you minus Q over C. Okay, so getting the signs, getting the minus signs right in this equation is important, right? And I'll make a separate video on constructing differential equations for LCR circuits. Okay, so that's that. And yeah, and then you've gone one complete round, so this equals to 0. So now, on top of that, right, if we do a quick rearrangement, we'll see that we're almost there, right? We have E equals to IR plus Q over C, but we're almost quite there, but the I needs to be dq dt, and in this case, it makes sense because imagine a positive current, right? Imagine the positive current I. I can't go further to the left. Imagine the positive current I, right? If this is positive, then that means the charge is flowing in an anti-clockwise direction, and it's increasing the charge, positive charges on the left hand of the capacitor, left hand side of the capacitor, which is denoted plus Q. So the fact that this I, if it's positive, then your charge is increasing, it ties in nicely with this definition. So if we had flipped the signs, right, of our current, then we have to introduce the minus sign over here. Yeah, so yeah, this is about a convention that that is wise to follow. So I always like to define my current such that I is dq dt, and there's no room for ambiguity. But I will cover the two cases in another video, right? Where I can write I equals to minus dq dt, and I'll talk about that scenario another time. Anyway, so substituting this back in, you obtain this equation. Okay, so show by direct substitution or otherwise that the solution to this is given by this. So since they told us to do direct substitution, that is the simplest method, right? So we substitute this into the differential equation, right? We get R. So R. So dq dt. Let's compute that. That will give us minus b over tau e to the power minus this, right? So this is going to be b over tau e to the power minus t over tau, right? And then q over c is just a over c plus b over c e to the power minus tau over t over tau equal to e. Okay, so with that, so we notice a few things, right? On the left hand side, we have a function of time. On the right hand side, we have a constant. So yeah, the fact that it's a function of time, and if you want both sides to be satisfied, right? If you want this equation to be satisfied at all times, right? This must apply for all times t, right? T equals to 1, t equals to 2, and so on, t equals to pi, and so on, must be satisfied at all times t, right? Then your coefficients must cancel. So what that means is that looking at the coefficients of e to the power minus tau, minus t over tau, right, which is this, right? You have your b over c minus rb over tau equals to 0. And looking at the coefficients of the constants, right? If this guy equals to this, so your a over c must equals to e, right? So from the bottom, we know that a equals to ce, right? So a, ce, right? Remember? Okay, so a and b are constants that we don't know yet, but c and e, right? C is the capacitance and e is the EMF. So a is actually just your max charge, right? So this just means that a equals to your max charge, Q max. Right? And on top of that, right? So solving this one over here, what do we get? We get b cancels out, right? Wait a minute. B. So okay, I'll show you what b does later. So b actually cancels out in this equation, and we get r over tau equals to c. Wait, no, hold on. We get r over tau equals to 1 over c, right? And that gives us tau equals to RC. Yeah, that makes sense. So this is known as the RC time constant, which remember, right? If you remember, okay, so remember over here, the RC time constant, it appears in the denominator, right? And yeah, so this is where it appears in the denominator of your exponent. So on top of that, right, we also need, so we have the function, we have found out A, right, which is turns out to be the max charge. We have found out tau, which turns out to be the RC, but how about B, right? So looking at the expression, right, you have Q max plus B e to the power of minus T over RC, right? So what is B over here? We need to substitute when time t equals to 0. So at time t equals to 0, how much charge is on the capacitor? Your Q should be ideally 0. Right? Your Q, this is your initial condition for your differential equation. So at the moment, right, B, so Q substituting t equals to 0 into this expression gives us Q at t equals to 0 equals to Q max plus B, right? Because e to the power minus 0 over RC is just 1. right? So that gives us B equals to, it should be 0, so B is minus Q max. So in total, right, you have Q max 1 minus e to the power minus t over RC. So that is your final expression for Q as a function of time in terms of the parameters. And Q max is just CE. So yeah, and you see that corroborates with my formula here, which I wrote just now. So actually, right, it would have been better if you do the derivation first, then you plot the graph, right? That's a logical procedure. So yeah, but in this case, you're asked to plot the graph first. So I suppose that's what we want. Okay, so using your equation here, find expression for I in the circuit. So as we know, right, since Q of t equals to Q max of 1 minus e to the power minus t over RC, right, and then your I is just the derivative of Q with respect to time equals to Q max minus 1 over RC e to the power minus t over RC. Actually it's both plus. Yeah, so the two negative signs cancel out. So so this is just going to be Q max over RC, right? E to the power minus t over RC, which if you look over here, right? Remember that I of t, we found out is Q max over RC, e to the power minus t over RC. This part matches, right? Then your maximum current is just Q max over RC. Yeah, so okay, I hope that's clear. So use your expression to determine the instantaneous power dissipated by the resistor. So I is a function of time, right? What I mean by instantaneous power is that power is a function of time. At this point in time, how much power is dissipated, right? And the answer, right, is P of t equals to I squared R. So that's just that. So it's just P equals I squared R, just that you put in a time dependence. And if your resistor dependent on time, then sure enough, it will be this. But in this case, I don't think our resistance is constant, right? So it's just that. So yeah. Yeah, so that's that. So substituting this into there, we just get Q max over RC. So Q max, right? Q max is actually CE, right? So actually this is just E over R, e to the power minus e over RC, right? Right, and then this thing squared times R. So one thing we notice is nice over here is that, hey, at time, your I max is equal to Q max over C over RC, right? Which equals to, so your current max is actually equals to E over R. So at time t equals to 0, right? This matches our intuition very nicely. Because at time t equals to 0, when your capacitor has 0 charge, right? When your capacitor has 0 charge at this time instant, right? Your capacitor has 0 charge over here, then that will mean that essentially it looks like a short circuit, right? And what's the current flowing through such a circuit when your capacitor is just a short circuit, when it's not there? At that point in instant in time, right, the current is just going to be E over R, because your C hasn't built up enough charge to develop a potential difference to kind of inform the circuit that it's there even. So for all purposes, right, at time t equals to 0, your capacitor is invisible to the rest of the circuit, which is why the current at that point in time is E over R. So that is quite nice. Yeah, so that matches our intuition nicely. And by expanding this out, right, you get E squared R, no, E squared over R, right, E to the power minus 2 T over RC. So that's the instantaneous power as a function of time. So so this term is just a constant over here, and this is the dependence on time. Okay, so yeah, so this is the power dissipated in the resistor. So what's the total energy dissipated, right? It's just going to be integral of this with respect to time. So the total power dissipated, T total, right, across all of time is just the integral of this from t equals to 0 to t equals to infinity, right? Because the capacitor is only done charging when it just asymptotes towards the fully charged state, right? It never actually reaches it. So when you put t equals to infinity over there, then yeah, so okay, I don't know why my pen goes to eraser when I do that. It's quite annoying. But never mind. Right. So the so it's integral of t of t dt, which if you do the integral, right? So it's integral of this thing, dt from 0 to infinity. So the integral is just rc over 2 negative sign e to the power minus 2t over rc from 0 to infinity, right? And that is equals to, so at time t goes to infinity, the upper bound, right, is 0. And the lower bound is just, so just gives you rc over 2, and that is just rce squared. And remember that, yeah, so that's total, that's final answer. And remember that this, we also derived over here, right, when we talk about the power dissipated in the resistor as a subtraction from the total work done by the battery, right, with the energy stored in the capacitor. So yeah. Yeah, so explain whether this result is an agreement. Yes, it is, because it is. Yeah, we just explained it. So it is an agreement, right? And yeah, so okay, so lastly, right, this is quite a long question. The switch S is fully closed. Okay, so let's continue with the question. It's quite a long question. We've got 3 more parts. So in the circuit below, the switch S naught is closed fully. It is closed to fully charge the capacitor C1 and C2 from the cell. Okay, then the S switch S naught is reopened, and after that, okay, so they give you the capacitance and they tell you to find the charge on the capacitor. Okay, so yeah, okay, so first of all, we know that okay, okay, so there are a few ways about going to do this, right? Okay, so yeah, so first of all, okay, my pen is really annoying. Okay, so when you close the switch, right, because this is 9.0 volts, right? So after fully charging the capacitors, the PD across the capacitors would be 9.0 volts. And so we have 9.0 equals to, what's the PD, right? It's the charge across Q1 divided by capacitance of Q1 plus the charge of Q2 divided by the capacitance of Q2. And this, yeah, so we have this expression. And we know C1 and C2, right? Because they're given the question over here, C1 and C2 is these two values. But what is Q1 and Q2, right? Now, because your current is flowing through the circuit like this, right? Where all the current that flows through C1 is the current that flows through C2, right? Yeah, so so as a result, right, the charge across Q1 is equal to the charge across Q2, because the only way for charge, if you have plus Q and minus Q developed like this, right, because your two plates here are isolated, if you draw, your two plates here are effectively isolated. Okay, it's very hard to draw between the two, but effectively, your two plates are, the two plates here, the conservation of charge, they must be plus Q and minus Q and plus Q like that. Right? And on the other hand, like that. So conservation of charge tells you that Q1 equal to Q2. Okay, and so from here we can say Q1, right, 1 over C1 plus 1 over C2. And from there, we know C1 and C2, so we can calculate Q1 equals to 9.0 divided by that quantity. Right? If you calculate it out, then Q1 is equal to minus 6, equals to 6.88. Right? times 10 to the power minus 6 coulombs. Okay. Okay, so my pen no longer stopped doing the annoying thing, I think. So that's good. Okay, so yeah, so that's that. So the charge on each capacitor, right, is going to be 6.88 times 10 to the power minus 6 coulombs, and 6.88 times 10 to the power minus 6 coulombs. Okay, so now we can calculate the PD by just using V 2 over C. Sorry for the thunder, right? And so given by substituting it in, we just get 2.75 volts and 6.25 volts. Another way to do this question is to do okay, never mind. Yeah, never mind the other way. Is to just find the effective capacitance, but yeah, effectively the same procedure. Okay, so now the switches are closed simultaneously. The fixed resistors, there's no current in R1, calculate the resistance of the variable resistor. Okay. So we're given that there's no current in R1, right? So wait, let me just take a look and digest the question. So okay, so if there's no current across R1, if there's no current through R1, right? No current through R1, then that means the PD across R1 is going to be 0 as well. So um, so if there's no PD across R, if there's no current through R1, right? There's no current through R1. Okay, so let's go ahead and label the resistances first. So over here we have 40, I think it was 40, we have 42 and 58, right? So this is 42 ohms and this is 58 ohms, right? And then on the PDs, right, you have your 2.75 and 6.25, 2.75 and 6.25. Okay, so that's the ratio of the PDs. Yeah, so okay, so if we do apply Kershaw's voltage law on C2, right? Okay, so first of all, so we know that current flowing through this blue part of the circuit, right? There's current flowing through this blue part of the circuit, and let's call it I. And the reason why we can call it I is because no current flows through R1. So effectively, whatever current comes in this junction, right, it must all leave through this junction as well. So whatever comes in here must go out here because no current is redirected into R1. So that's why we label it like that. And then looking at the second loop, right, looking at this loop, if zero current flows through R1, that means the PD across R1 must be 0. So if the PD across R1 is 0, then that means the PD of your C2, right, must be the PD of your R2 or your resistor 2. So with that, since we know the PD of C2, right, equals to 6.25, and we know the PD of R2 is I times 58 ohms, right? Then we can solve for I to be equals to 25 over 232 ampere. Okay, so yeah, so given this, right, likewise, if we want to find, now we can consider another loop, right? The other loop would just be this loop over here. So now we're considering this loop like that, right? So the likewise, right, the going the Kershaw's voltage law will tell us that the PD across C2, right? So PD of PD of C1, right, is equals to the current times the resistance that we don't know. And we know the current is this value, so we substitute it in here. So we have 2.75 equals to 25 over 232 times R. So the variable resistor we don't know, right? Then R variable equals to, solving for it, we get 25.5 ohms. So that's how we calculate the variables, the resistance of the variable resistor. So yeah, so with that, that's 25.5, and we are done with question 8.